have a look at this. Let's come back to our choice of L. Okay. Now we had our original system. There was L transpose AL. Right. This was our A hat. So now again we are going to pull one rabbit out of the hat. There is a very nice theorem from linear algebra which gives what is called a Cholesky decomposition of a matrix A. You may or may not have heard of it. So let me write it down. You can look it up. So Cholesky decomposition of a symmetric positive definite matrix A is a very nice result. CC transpose. Okay. So CC transpose where C has some property. What is that property? Has anyone heard of the Cholesky decomposition? C is lower triangular. C is lower triangular. Okay. Now this C being lower triangular, let's have a look once again at our L transpose CC transpose L. Let's say that I had my this was my A hat, right? So what would be the ideal choice that C should take, or rather L should take? Let me put it that way. Supposing I knew the Cholesky decomposition of A, what would you choose as L? If I can make this into identity, I am done. So the best thing would be that L transpose should be equal to C inverse, right? Then I would be done. Of course, Cholesky decomposition, exact Cholesky decomposition is almost as expensive as calculating Ax equal to B. So we are once again back into the same situation. Looks nice on paper, I can't use it. Okay. However, here comes the real rabbit out of the hat. There is something called the incomplete Cholesky decomposition, okay, which says that A could be approximately written like this, kk hat, where k has a very interesting property. K is very similar to C, okay, in the sense that so what is K is a sparse lower triangular matrix. Okay. So it does not agree with C completely. That means if I calculate, for example, this, the Frobenius norm of this means entry wise take the root mean square, what will I get? I will not get 0. So it's not a exact, that's why it's called the incomplete Cholesky decomposition. So it is cheap to compute, okay, and that's why it is used in this way. Supposing A is, I do this incomplete Cholesky decomposition, it is still a lower triangular matrix, okay, but it's also sparse. So there are some disagreements over there, and you can make this incomplete Cholesky decomposition less accurate or more accurate. This is a very, very powerful tool in linear algebra, to the extent that there is a inbuilt function in MATLAB called iChol, right, which, and you can give it some threshold to make it less accurate or more accurate. So it's standard, you can readily apply it to your problems, okay. So supposing you did this incomplete Cholesky decomposition, you got your kk hat, right. So how does that help you? So if this is done, so now comes to the practical case. Now I can choose my L transpose to be what? Exactly like before, right. So here I had chosen L transpose to be C inverse, which we said is impractical because it's as good as having solved the problem. Now I have relaxed my requirements and say, okay, fine. So L transpose is equal to K inverse, okay. So far it's good because K is inexpensive to compute, right. Correct. Now the question is, what about K inverse? K inverse may not be very nice, right. So actually we don't need L transpose. What do I need to solve? let's go back here. What I need to solve is this guy. LL transpose RK equal to YK. So let's plug that in over here. So LL transpose RK is equal to YK. This is what I need to solve, which will become K inverse K inverse transpose RK is equal to YK. That's what I need to solve, right? So this is how can I write? Can I simplify this further? So I can take this to the other side, right? So what will I get? I will get RK is equal to, there's going to be a K transpose K YK. Is that right? Or did I get one transpose wrong? If I left, is this expression correct? Oh, it's sorry, this is what is wrong. So L is actually, so if I write over here, so L is equal to K inverse transpose, right? So this is where I made the mistake. So this is going to be K inverse transpose multiplied by K inverse RK, right? So what do I do next? Inverse and transpose can be swapped, right? And what I am going to get is RK is equal to KK transpose YK, right? So this has to be solved. Now when I asked to compute the Cholesky decomposition of A, what was given to me? KK transpose. KK transpose is appearing right over here. This has been given by incomplete Cholesky. I don't have to calculate inverse of a matrix anywhere. Okay. So that's the first. So that's the first advantage, right? No need. Coming to that. We need YK, right? So first thing is no need to compute this thing. Now here is, I mean, this is why this whole idea of preconditioning with incomplete Cholesky is so clever. I need YK, right? Because RK I can compute. Why? How do I compute RK? A times xk minus b. If I know I am at x naught, A x naught minus b I can compute. I got my RK. But I need, according to this expression, YK. How can I cleverly solve this equation without having to spend order n cube in inverting KK transpose? The hint is the structure of K. What is the structure of K? It's lower triangular, right? So if now, let's look at this a little bit. This is K transpose YK. Supposing I combine this and call this ZK, right? So therefore this is equal to KZK. K is lower triangular and sparse. It's like this. Do I need to actually invert this, or is there a clever way of solving this to get ZK? Visualize this matrix. The shaded part is where the numbers are non-zero and this is 0. Huh? Something much simpler. You could, so if you saw this matrix in class 12, you could solve it. What is it? Back substitution, right? The lowest, I mean, for example, Zn, right? Is it available immediately? This entry, supposing this is being multiplied by Z1 up to Zn, right? Zn in one, sorry, not Zn, Z1. Z1 I will get Z1 times capital K11 is equal to B1. I am going to get Z1 in one shot. Z2 how will I get? Same thing, back substitution, right? Because Z1 is known, Z2 I will get. There is no inversion happening. This is simple algebra, right? This is called what? Forward substitution, I think, right? I get confused. One is called forward substitution, the other is called backward substitution, right? Forward probably because you are starting from Z1 and going down. So let's call this forward substitution. I may be wrong. So I get ZK cheaply. Okay, and it's a sparse matrix, so I don't have to actually calculate every single thing. The number of operations may be actually even lesser than a dense lower triangular matrix. it may not be O n cube. Well, okay, it will be, this will be of order n squared if it were dense lower triangular, because there are, each one is getting multiple. This is similar, this is similar, exactly similar to LU decomposition, but the decomposition, the price of decomposition was n cube. Here I am giving you the decomposition at a cheap price. Having got the decomposition to get the solution is not n cube. The LU decomposition is n cube, Cholesky decomposition is n cube. Incomplete Cholesky is not n cube, that's the catch, right? So I have got Zk. Having gotten Zk, how do I get back Yk? This will not be order n squared also, because it's sparse, right? It may be like n log n or something. K transpose Yk equal to Zk. I know Zk from forward substitution. Can I get Yk cheaply? What is the structure of K transpose? Upper triangular, right? So it's like this, and this is 0. Now what do I, from which order do I start? I'll start from Yn, right? So I will start from, so this is going to be my Y1 up to Yn. If I start with Yn, right, Yn times Knn is equal to Zn. One shot I get my Yn and I move back. So this is why I would call this back substitution. Okay, and that gives me my Yk, right? Very, very elegant. And finally, I mean, this does not need to be said, but do I have to calculate a new incomplete Cholesky decomposition at every iteration? No. Given A, I get Kk, I am with that Kk for the rest of my iteration. So all I have to do is one time cost of computing Kk transpose, and then forward substitution, back substitution. It's very, very quick. That gives me my y's, right? Once I get my y's, if I scroll back over here, I got my P0 in step 7. So I know the first conjugate direction, it's minus y0, right? Once I know my y0, then I know my next P is also calculated from step 6. Betas and alphas are available over here. Now you notice the expressions are very nice in terms of yk plus 1. Everything is available with me, right? So the update equations are the same. The only places in the code where I have to modify is new expressions for alpha k, beta k. One additional step of solving this forward substitution and back substitution. You should be very careful to put your incomplete Cholesky outside the while loop. A one-time step to calculate Kk transpose, that's stored, and then that's used every time in each iteration, right? If you put it inside, then you would kill yourself. Correct, right? So when we look at here, Rk is needed to calculate Yk, right? This final discussion which we had, we needed Rk to get Yk. Any other questions? Ruben. Any part that's not clear? Should we walk through it again? We have starting point. Okay, let's look at our start. Let's try to write this now. Summary. So what are we given? You gave me A and B, right? And what did I say? I said bad condition number, okay. So then what did I do? I took A and I did not equal to, approximately equal to Kk transpose, which was what? I am going to use the MATLAB name for it, iChol, okay. This is cheap, fine, yeah.
Rk can be simply calculated as Ax by
it is.
But then why do we need this Kk transpose?
Which equation? We are never inverting it. We're just calculating it.
Yeah, we did forward and back substitution. Like RK equal to LL transpose YK.
No, it's wait. Here, this expression. That is the expression we are looking at. In terms of, because L and K had an inverse relationship. Okay, so step 1 is this. Step 2, what do? I am going to pick a random or your choice of what? X naught. Fine. This is your wish. What would be the next step? I need to now know I need to move, right? So, I need to get P0, right? P0 was equal to what? Minus Y0. To get Y0, what am I doing? Solving. This is that equation over here. R0 is equal to KK transpose YK. R0 is equal to KK transpose Y0. How did I get R0? Simply AX naught minus B, right? So, I can do this by, let us give it a nickname, forward substitution, back substitution, FB. FB gave me this. So, I got my Y naught, minus of that gave me my P naught. What is the next step that I need? Alpha, right? I need alpha. Alpha, so an expression for this, right? Expression for this was what? RK hat YK divided by PK transpose A PK, right? So, at this point I need R0, Y0, P0, A, P0. Do I have all of these? Done. So, I have this. Next step would be, I have got my alpha, I have got my P0. Where can I go next? I can go to my next x, right? So, I can write xk plus 1 is equal to xk plus alpha hat k pk. Remember, I am not writing this from first principles, I am writing this after that worked out expression. Otherwise, if I were naively writing this, I would put hats on everything, but I simplified that to simply this. So, this is what I got. Do I know everything here? Yes, I do, right? So, I have reached my new xk plus 1 I reach.
What will be the A which you are using in
The original A, that is what we worked out. We can do more work, but we do not like to do more work. This is the original A. When we started with the very first step, if you notice, this originally this expression would appear everywhere, P hat transpose A P hat, but this is actually nothing but P hat transpose, sorry, this is with this choice over here, this expression would be simply equal to Pi transpose A Pj, if you substitute it, right. So, that way I avoid calculating some new P hat, because remember, for new P hat I need this L inverse, I do not want to get into any inverses, right. So, alpha hat is done, it is the original A, xk plus 1 is done. Before I go to the next iteration, I should be careful to calculate what? My beta, I mean, so that I get my pk plus 1 for the next iteration. So, I will use my beta k expression, which was also in terms of r's and y's, right. So, this was rk plus 1, sorry, not hat, rk plus 1, yk plus 1, rk transpose yk, yeah, that is right, right. Again, can I calculate this? Can I calculate rk plus 1? Yes, because I know my new xk plus 1 from the previous step. So, I can calculate my rk plus 1, and I need yk plus 1. Can I get yk plus 1? Yes. Why? Because I know r, I know the kk transpose, and I know, therefore, I can get y. So, all of this can also be done, and as a result my pk plus 1 update expression also goes through, which was pk was equal to minus yk plus beta hat k pk minus 1. Now I know everything over here. I know my betas, I know my y's, I know my previous p's, I can go to the next p, right. So basically, if you look at now this, what we have done so far, my earlier CG routine needed minimum modifications. In some places, I just had to substitute, write this y character in two places. Other than that, this, apart from this extra step of forward backward calculation for getting my y's, it just goes through. Okay. So this is the entire preconditioned conjugate gradient method. It's a very beautiful piece of linear algebra working at at a low cost. And this, because if you look at, I really encourage you to look at the MATLAB documentation of this incomplete Cholesky. They actually give an example of how to speed up CG in that, in one of the examples. It takes in several arguments. You can even increase the threshold to make this more and more accurate. So remember what I wrote over here, this expression. How different is it from A? You can make it closer and closer, or you can make it coarser or coarser. So the more effort you expend into this, that's price paid, but your condition number is falling more and more, right. In the ideal case, if this actually became the Cholesky decomposition, your basically your condition numbers become 1. That's as good as it gets. So obviously that's not worth it. So you may as well do, right. So this is, if you look at any standard numerical linear algebra routine for that implements the conjugate gradient method, no one will have it plain conjugate gradient. Everyone will have a preconditioned version of it. And in the market, there are several preconditioners. We just spoke about one of them. Okay, and all of them are based on some one small or a few small clever tricks of linear algebra. Okay, which is why linear algebra is a very strong prerequisite for optimization. Good. How are we on time? All right.
Conjugate gradient and preconditioned conjugate gradient both are overflow algorithms, but the latter is much faster. That's because of lower condition number.
I would not say that both are order n cube. Solving Ax equal to b as a direct method will be n cube, but we are not doing a direct solve. We are doing an iterative solve. We are going iteration by iteration.
At most it requires n steps, and each step.
At most it requires n steps, and
at each step we have n squared computations, right?
why n squared computations? My k is sparse lower triangular.
But I have APK, right? You have PK transpose into APK.
Oh, computing that. Yeah, in that sense it is n squared. But there, so that I want to put a little bit of grain of salt over there. If I can multiplying two vectors, let's say two n length vectors, according to you, is that a n squared operation? It's a n operation and there are n of them, so n squared. If it's a n operation, that means this multiplication of this, each of them is happening serially, that is how you are saying n. But if I have vectorized code and a vectorized hardware that does it, it's actually order 1. Right? So that's why this becomes into how properly is your algorithm recognizing the underlying hardware. And with distributed cores, multi-cores, multi-thread and all, it becomes very hard to make a definitive statement that this is definitely order n or something. It can be lower.
Can't use the same argument for conjugate direction method too,
Conjugate direction method, there the trouble was computing p itself, because conjugate direction method, either you did Gram-Schmidt or you did you could parallelize it there, but every step that you could parallelize in conjugate direction method, you could parallelize here in the conjugate gradient method. It's not the same, because the amount of parallelization required over here is to bring n squared down to, let us say, n. That would bring n cube down to maybe n squared log n or something. So that gap will kind of remain there, right? But at the end of the day, it boils down to actual implementation, how cleverly and how nicely it is done, right? Which is why you'll be surprised to know that a lot of very serious numerical linear algebra routines in the physics community are, for example, written in Fortran to this day, because it's one of the most efficient languages. Has anyone ever coded in Fortran? One. It's a beautiful language because it's so simple. It's like C, but it doesn't have any of the memory allocation nightmares. It's just, you have to write everything out explicitly. There is no high level abstraction there, and so it works blazingly fast. So C and C++, at best they come as close to Fortran, they never beat it. So that's kind of the gold standard, right? Very old fashioned, but you look at the codes written, for example, in your high energy physics, the Higgs boson discovery and all of that, underlying it you will find Fortran code. LIGO gravitational waves observations, with high chance you will find Fortran code. Okay, so sometimes old is gold. All of the new languages, I mean, the other end of the spectrum is Python, right? Just it'll take forever and ever.
Even if the condition number is 1,
Hmm.
it can still take n steps, right? CG can still take n steps.
At most, I mean, if condition number is 1, A is identity, you have solved the problem. X equal to B.
So, like, we know any CG method will work, it will give the solution exactly in n steps.
Hmm.
So, if condition, if like nicely condition matrix is also like taking at most n steps, and with respect, when compared to some other normal matrix, why are we even bothering to like reduce it?
No, okay. The reason for this is the first graph that I showed in the class. So this is as I'm increasing the condition number. At most n steps was like a ideal result, right? Where we did not even mention condition number. In the real world, this is the situation.
If we have enough resources to like at least spend n steps, then we don't need to.
Correct, correct. Which is almost never the case. Often, I mean, in many, particularly like in ML like applications, I don't want to drive the error down to 10 to the minus 16. I'll work with 10 to the minus 4 or 5. And for that, if I can just improve the condition number a little bit, I spend fewer iterations when doing it, right? So it's all a very, very, you have to take a composite view of what are the resources at hand, what do you need to speed up and what not, right? You cannot win on every front. Somewhere you have to give up, which is the other name for engineering, right? Okay, so this is it as far as question.
How do you know the condition number of
How do I, okay, good question. How do I know that the condition number of A hat is less than that, right? So the argument is a little bit roundabout. If I did a perfect Cholesky decomposition, the condition number becomes 1. That you agree? We showed that, right? If it is equal to. So now I back off from perfect Cholesky decomposition to incomplete Cholesky decomposition. So there the reasoning is that because it's incomplete, this product is not going to be identity, it's going to be something short of it. So with a controllable threshold, which is an input argument to the Cholesky algorithm, you can sort of have a knob on the condition number. We are not proving it, but it is numerically found to be the case. So that's the knob that I have. So how much resources are you willing to spend in your incomplete Cholesky? Gives you that much better of a condition number. But if you spend too much on it, then it's not worth it. Okay, so you can play around with this in iChol in MATLAB and see that as I change the thresholds, it takes more and more time. Then at that point, it's not worth it. Okay, so you already have the CG code from the class from last time. So you can see modifying it for this is a few lines, that's it, there's nothing much to it. So when you are faced with applying CG to your research problem, right, it's going to be trivial. And then the next step, the next module that we'll look at, which is the nonlinear CG method, by the end of it, you will have modules ready for everything, for preconditioning, step length using backtracking and Wolf conditions, everything put together. You will be able to tackle your first nonlinear problem with all the nuts and bolts already there, just. Okay, good. Any more questions?
Sir, why can't we take orthogonal matrices L? L transpose will become identity, may not be identity even any other diagonal matrix.
Why don't we take any other diagonal matrix?
Not diagonal matrix, orthogonal matrix.
Orthogonal matrix. You mean orthogonal, mean all the columns are perpendicular to each other. You have to prove that that's actually improving the condition number. Otherwise, I mean, for example, if it is a rotation matrix, no use. It may just rotate the eigenvectors. Eigenvalues will remain as it is, so it may not help you, right? So there are other cheaper tricks also. For example, there's a diagonal preconditioner. So you just take the, I may be wrong, but I think if you just take the A matrix, take the diagonal elements and invert them and create a new this thing over there. That. Correct. Yes, lots of tricks are available. Depending on if you know something about the structure of A, this is very crucial. If I know something about the structure of A, I can leverage that information into getting a good preconditioner. So in the market, you will find general purpose preconditioners that don't care what A is. And then there are these fine-tuned ones. For example, if A is toplets or this or that, then you have some more tricks that you can do. Right? So these two worlds are very closely intersecting, linear algebra and optimization.